So now from this lecture we want to talk about homotopy. As we have mentioned earlier that in topology we want to classify spaces as much as possible, and one of the possible ways was to finding holes, and from there we had the idea of the homology groups, and now we'll discuss the idea of the homotopy. So let's consider a motivational example first. So this is a motivational example. Let's consider a space R2 and consider another space R3. Geometrically, if I try to draw this, R2 is just my xy plane, and R3 would be my 3D space. Now, my question is that the question that I'm interested in right now, let's say, is that how do we distinguish between these two spaces, that is R2 and, sorry, not and, it should be R2 with R3 topologically. Okay, now we can make it even more interesting by deleting the origin. So instead of having the origin over here, the O, let's say, now we delete it. What do we mean by this deletion? Well, instead of 0, now you have nothing over here, so let's put a O, big fat O. Okay, this means the origin is deleted, and same on this 3D space. Now let's draw a circle in the xy plane, or say a closed loop. If you draw a circle, or so to say S1 over here on R2, then if this circle encloses this origin, the deleted origin, then if you try to shrink it to a point, you will realize that you won't be able to do that without leaving this R2 space itself, right? Because there is a hole over here. So you may shrink the circle like this, but you can never shrink this circle that encloses the origin or the deleted origin to a point. However, if you have a circle over here, you have no problem at all to squish it and turn it into a point like this, right? But consider this same circle S1, but now it's on a R3 space, right? Now this space has an extra dimension than R2, so we can use the extra dimension, or we can use the benefit of it to translate our circle like this, either in this direction or in this direction per se. Then if I translate it, now after translation, this is where the circle ends up at, and now you can continuously shrink the circle to a point. So we can see that if I have holes in these two spaces, and yet I could distinguish them by taking a circle and asking the question whether I would be able to shrink it to a point without leaving the space itself. So instead of 2 and 3, what you can do in general is that if you want to distinguish between Rn, let's say, and Rn plus 1, then the idea is that can you continuously shrink a Sn minus 1, that is a circle of a sphere of n minus 1 or n minus 1 sphere. That's how it's pronounced. It means that the surface of the sphere is a n minus 1 dimensional surface. So if you want to distinguish between Rn and Rn plus 1, the idea is that you have to ask the question that can you continuously shrink Sn minus 1 to a point in both of these spaces. So this is a way. That means again these holes are ways to distinguish between spaces, right? So again, when we discuss homotopy, we will see that these holes will again lead us to some new tools, and it will give us some tools that will be very interesting, and from there we will define what homotopy is, and we will see that this homotopy thing will have a group structure itself, and those are our homotopy groups. And now let us start with some definitions. Again, to develop the idea of the homotopy groups, we will need to have some definitions, or so to say the development to develop the topic itself. So we'll start with some definitions, and once all the essential definitions and tools are given, then we'll jump into the computations.